overdispersion can occur when there is more variability in your response variable than what is accounted for by your regression model. We do not want to have overdispersion occur because that is a sign that the model doesn't fit the data very well. It can also lead to inferences that are too liberal. Now, overdispersion can occur with any of the types of models that we've talked about so far, but in particular, it occurs most often with respect to Poisson regression models, so that's what we're going to focus on here. Now, the reason why it occurs often with Poisson regression models is because with a Poisson distribution, if we have a random variable y that has a Poisson distribution, the expected value of y is set equal to the variance of y. So the mean is equal to the variance. Now, what will sometimes happen is if you were to, let's say, find the sample mean of your observed y values and also the sample variance will be much more than the sample mean. When that occurs, you have overdispersion. To see how this can be detected, let's say in an ad hoc way with respect to the horseshoe data set, the horseshoe crab data set, excuse me, let's take a look at the following code and output. So we read in our data, and what I'm going to do is create some groups for my data corresponding to the width of the shells. A quick way to do that is to use in R the cut function, where I grab the width out of the crab data frame, and I'm going to essentially, you could say, cut up my data based upon the following width categories: 20 to 23.25, 23.25 to 24.25, and so on up to 29.25 to 34. So essentially I'm going by one, where on the outer limits I allow my group size, my group range to be larger, just so that I capture everything by width. And I'm going to put these groups then into the crab data frame in a variable called groups. And this is what we get when we take a look at the first 5 observations. So for the first female horseshoe crab, it had a width of 28.3. There were 8 satellites, and it fits in my group of 28.2 to 29.2. These little symbols here, that 29.2 means less than or equal to 29.2. This symbol there means greater than 28.2. Now that I have these groups, how about we find the mean for each of the groups, the sample mean, and also the sample variance. So to do that, I go back to the aggregate function that we've used a number of times before, where I want to aggregate the number of satellites by the group. Data's in crab. The function I want to apply to each group is mean. Put that in an object called ybar. I'm going to create an object called yvar, which is found exactly the same way, except for I'm going to put var for variance there instead. So the var function finds the sample variance. And then let's summarize this all with a data frame. And this is what I get. So for example, for the group of 25.2 to 26.2, the average number of satellites per female crab is 2.69. The variance of these number of satellites is 11.38. And so we can see that the variance is much bigger than the mean. This is indicative of you have an overdispersion problem within the data itself. Now, if we didn't have overdispersion, basically you would expect then that sample mean to be approximately equal to that sample variance. So, when the variance is larger than the sample mean, we have overdispersion. Dispersion is a word that often represents variability. Over means more. You have more variability than what you would expect. This then is a violation of what a Poisson distribution, thus then eventually a Poisson regression model, assumes. This then will lead to potentially incorrect inferences. So what can you do then if you find that you have overdispersion? The number one by far thing that you should do is to try to find other explanatory variables to include in a Poisson regression model that helps to explain this extra variability. So for example, maybe it's also important to include the weight of the crab in a Poisson regression model with the width of the crab. That might allow this extra variability to be accounted for by width. It can explain it. Now, there are also two special situations where the data itself has a special format to it that will then allow you to account for the overdispersion. First, you can check to see if you have what's called a zero inflation problem. What that means is sometimes with count data, especially with a Poisson in a Poisson situation, you can have a lot more zeros than what you would normally expect, and that could be the cause of having this extra variability in your response. So when I say a lot more zeros, what I mean is a lot more zeros for the y's. In chapter 4 of my book, I talk about how to handle that situation. Now also sometimes you can have actually some dependence in your data, and that could lead to extra variability. When you do have that dependence in your data, one common way to account for that is to use what's called a Poisson generalized linear mixed model. So we've talked about generalized linear models. The mix there corresponds to adding what's called a random effect to the model. And that random effect helps to take into account this dependence that might occur for some observations. If you want to know more about that, that is a topic in my chapter 6 of my book. Now, if 1, 2, and 3 do not work, or look for 1 again, that's the most important thing to do. There are certain situations where 2 and 3 will work. If you have no other choice, then try 4 and 5. And this is often what can happen. Number 4 corresponds to a quasi-Poisson regression model, where you make some of the kind of assumptions of a Poisson regression model, but you allow there to be extra variability in it. You'll see how that is done shortly. You can also use what's called a negative binomial regression model. Negative binomial corresponds to actually another probability distribution that deals with count responses, and that this particular distribution allows you to have more variability in your response. We'll take a look at that later as well. So how can you then, let's say, detect overdispersion? I talked about one ad hoc method, and that can work fine, especially if you just have maybe one explanatory variable. But in many situations, you have more than one explanatory variable, and you still have some, you want to detect to see if there's overdispersion. And so one thing that you can do is look at that deviance divided by degrees of freedom statistic, DF for degrees of freedom. This statistic can be used for other things too, but what this measure allows one to do is see that overall for your model, is there some kind of problem? One potential problem could be this overdispersion. Now, what I like to do the most is to use a nice plot to help me see if there's overdispersion, where I could plot, let's say, the standardized Pearson residuals versus mu hat. And if I see a situation where I have a lot of points that seem to be randomly scattered about, and a lot of them seem to be above 2, or above 3, or below -2, below -3, this tells me I have more variability than I would expect in this situation, as long as a standard normal approximation will be holding. And so that's a key sign that myself and others look for if there is indeed an overdispersion problem. So let's take a look again at this horseshoe crabs and satellites data set, and let's estimate a model that we've seen before where we use the number of satellites to estimate then the, where we use the width of the female crab to estimate the number of satellites. We summarize the fit. So for example, here is beta hat 1.16. We've done this before. So to calculate this deviance divided by degrees of freedom statistic, what we can do is pull out the residual deviance from mod.fit by looking at the deviance component of mod.fit. We can also pull out then that corresponding degrees of freedom. And so in other words, if we take 567.88 divided by 171, we get 3.3. Now if we do that plus 2 standard deviations from 1, plus 3 standard deviations from 1 that we've seen previously, we can see that, at most we would hope that this statistic is only up to 1.32. And so we can see that we have a lot higher value for this deviance divided by degrees of freedom statistic than what we would expect if this model fit well. Excuse me. What about a residual plot? So what I could do is from mod.fit, my fitted.values gives me all my mu hats. Of course, I could also use the predict function to find this as well. Then I can use the R standard function to get the standardized Pearson residuals. I put them in an object called stand.resid. Then let's plot the mu hats versus the standardized Pearson residuals. Put some nice labels on the plot. Let's also put some horizontal lines on the plot as well using the AB line function. And so this is what we get. So down here, things are looking okay, but up here, things are not looking okay. We have many more standardized residuals outside, or let's say greater than 2, than what we would normally expect if this Poisson regression model was doing a good job. So this indicates to me then that I have a problem, and when I see this kind of an issue, I would think overdispersion. Now you might be thinking, well, wait a second, it's not exactly what we saw here before. I don't have the stuff here. But it's still the same idea that we have a lot more variability across the different values of mu hat than what we would normally expect. Now one could go a little bit further and look at, well, how many of these standardized Pearson residuals are greater than 3? I have 10. And we had a total of 173 observations in total. In the end, this means that I have about 5.7% of my observations greater than that, which is much more than I would expect if everything worked out. In fact, I would expect, less than 1. Okay, so how can we handle this overdispersion problem? We're going to talk about that method number 4, which corresponds to a quasi-Poisson regression model. Now, to help set this up, is think about how parameter estimates come about. For maximum likelihood estimation, we use a log likelihood function, and if we were to do everything in a nice mathematical manner, we would find the derivative of the log likelihood function with respect to a beta, a regression parameter model. In fact, we would do that for all of our regression parameters in our model. And so we have this right here. And again, this is for all the regression parameters. So we have p plus 1 of these. We would set each of these equal to 0, and through using numerical iterative methods, we would, numerical iterative procedures, we would solve these equations for the betas. The solutions end up being our beta hats. Since we are working with these equations to try to find estimates, these are referred to as estimating equations in statistics. Okay, we'll come back to this shortly. Now, quasi-likelihood methods have a long history, and the basic idea behind them is to assume a particular kind of relationship between the mean and the variance, but not necessarily assume an overall distribution for your response variable, let's call it y. So in this particular setting with a Poisson quasi likelihood, or using a Poisson regression with a quasi-likelihood, what we're going to do is assume this relationship between the variance and the expected value of y, where the basic idea is that I'm going to have an additional parameter in there, gamma, that's going to allow the variance to be higher than the expected value of y. So for example, if gamma is 2, that says the variance is twice the expected value of y. A regular old Poisson regression setting, or Poisson distribution setting as well, would just assume that gamma was equal to 1. Okay. Now let's think back to these estimating equations before. In a Poisson regression setting, one could actually go through the math, and for students in my class, once they're not responsible for doing this, go through the math, and for each of these partial derivatives of a beta for the log likelihood function set it equal to 0, you end up with this particular expression here. So y is our response variable. Mu then would be our corresponding model for the mth observation. Notice the beta is in there. X would be then the corresponding explanatory variable, or one of them. There's the mu again, and we would divide by the variance of y. This again comes about through actually taking the derivative of the log likelihood function for a Poisson regression setting. Then, what is the variance? Well, the variance is equal to mu for Poisson. So notice what happens. This simplifies, and this is what the estimating equation gets. You would set this equal to 0 and solve for the beta for each of your betas. Now, what the quasi-likelihood approach does is says, okay, let's take that same kind of setup, but what we're going to do is replace that variance with gamma times mu sub m. Again, we have some simplifications that occur. Notice how the 1 over gamma pops out. And so we have exactly what we had before with regular old Poisson regression. But now we have a 1 over gamma out in front of it. What we're going to do for each of our regression parameters is we're going to set this equal to 0, solve for the beta. You're going to have to use numerical iterative procedures for that. But since we're setting this equal to 0, look what happens. I can multiply both sides of my equations here by gamma, and the gamma goes out. Okay? So in the end, the exact same estimates for the betas will actually result for a Poisson regression model. But then when one goes further and works with, let's say, an estimated covariance matrix, this gamma doesn't actually disappear anymore. And instead, the estimated covariance matrix for our regression parameter estimates is exactly the same as what you would have with a regular old Poisson regression model, but now multiplied by gamma. This gamma then allows more variability for your beta hats, and then this will also then end up helping your inferences that then eventually involve your beta hats, because we take into account this extra variability. We could use various measures of model fit or various other inference methods, and we're going to see a very similar thing happen where, for example, here's a standardized Pearson residual, and notice it's exactly the same as before, but now we have this extra gamma in there. Well, how do we know what gamma is? Well, it is a parameter, and it needs to be estimated. The standard approach that people use is to, let's say, take your Pearson statistic, divide by the degrees of freedom for the residual deviance degrees of freedom that we saw previously, which is also the same as for the x squared statistic, and use that then as our estimate for gamma hat. Okay. We can do likelihood ratio tests as well. And they use a -2 log lambda-like statistic, just with this different definition of stuff, where we take our usual lambda, but now divided by a gamma hat. This changes the overall distribution approximation that we have, and instead now we need to use an F distribution with it. And then we have corresponding degrees of freedom associated with it as well. The regular old AIC cannot be used now since it's not a fully likelihood-based approach, but instead there is a QAIC that can be used. And basically it's the AIC divided by gamma hat. Do note that one should not, let's say, compare a QAIC with an AIC itself. Only with other QAIC values should this, only for models fit by quasi-likelihood should you use these QAIC values and compare them. Okay, so let's go back to using the horseshoe crabs example again and see if this quasi-Poisson regression model helps. So the code to estimate this model is the same as before, but instead of using Poisson here, we use quasi-Poisson. I'm going to put the results into mod.fit.quasi. Here's the corresponding output. Here's my beta hat 1, and that is exactly the same as what we had previously. Now what's different is that we have some information here about a dispersion parameter. That's just R's name for gamma hat. And to see the effect then that this gamma hat has, what we can do is take a look at the estimated covariance matrix for the regression parameters. So here's the var hat of beta hat. And what we can do is compare that to var hat beta hat 1 for the Poisson model. This is quasi-Poisson. And if you were to take this value times 3.18, you would get this value right there. And so you can see the effect that this has. We have more variability in our data than what we would normally expect for a Poisson. So how about we just allow the model now and its corresponding covariance matrix to have more variability as well to account for it. Now with the ANOVA function, if I say test equal F, then I can do my regular old likelihood ratio like test here. And so we have sufficient evidence, because since this p-value is very small, we have sufficient evidence that indeed width is important here. We could also find then corresponding confidence intervals, such as a walled confidence interval for beta 1. And if I use confident.default, object equal mod.fit quasi, parm for the parameter, the beta corresponding to width, level 0.95, R will find then the corresponding interval. We could use then this interval for beta 1 to find then the corresponding interval for the percentage change value. Now what's important to note here is, I guess I got a little bit ahead of myself. Here's the profile likelihood ratio interval that we had previously with just a regular old Poisson regression model, 13.28 to 22.51. Notice how much wider the interval is now, because now it's correctly taking into account that we have more variability. We could also do, I guess I gave you the profile likelihood ratio interval there. I should have compared it to the profile likelihood ratio interval here with the quasi-Poisson model. Same conclusion. We have a wider interval. Okay, so here's my estimated model, same as what we had with regular old Poisson. Let me take a look at the notes here. I think I've covered everything. I just give you some more additional details about comparing the variance from the Poisson to the variance for the quasi-Poisson results. How about a residual plot? So the corresponding codes in my program, similar to what we had before, we don't have stuff down here. In fact, now we have the point's a little bit farther away from that -2 line. But also take a look at what we have here. We have many fewer observations that are outside our plus or minus two, outside the +2, outside the +3 boundary lines there. And so what this quasi-Poisson regression model is doing what we want it to do. It's taking into account the more variability, and then when we look at plot of the standardized Pearson residuals, we have less evidence of that there's any kind of problem with the model's fit. Okay, so this is how to use then a quasi-Poisson regression model to take into account overdispersion.